Hello and welcome back to Aunt Rosie's Topological Bake Shop. So today we're going to be baking our quotient version of our monster donut, which is of course the 196882 Taurus. So here are the ingredients that you're going to be needing. Alright, so let's get to baking. Okay, so I have my baker, and of course grab your pen if you're choosing, and let's begin the recipe. So step one is you're going to grab your R1 spaces, or R1, so the real numbers. You're gonna grab your R1 spaces and you're gonna turn them into this product. So 1, 2, 1, 9, 6, 8, 8, 2, because of course our donut exists in 19688, 3 dimensions, and we're gonna be modding out this product by an equivalence relation to get a quotient space. And I'm aware that this is technically a product based thing, because of course if we don't do this product in the first place, we won't be able to construct the quotient topology, or it wouldn't be in the dimension that we want it to be in, so it wouldn't hold as much flavor without the product in the beginning. But nonetheless, it still employs quotient topology, and that's what matters in this variant of our monster donut. So we're gonna take this amount of products of R1, so it gives us R1 cross itself 196882 times, and I am going to denote that via R to the m-1, where m is the dimension of the monster group, which is 196883, because it will be extremely cumbersome for me to keep writing 196883. And again, I said a while ago the reason why I reduced the dimension by 1. Okay, so you can start with this dimensional space in order to completely avoid the product topology, but I'm just gonna make it apparent, or we're gonna start from R1, just to see how we got to R to the m-1, right? Okay, so now you may be thinking, okay, why don't we equip this with the product topology and then we're gonna follow on, but we can do that later, much later. So we can first define the quotient topology, but you can choose to start defining the product topology here, and then make that a topological space, and then take the quotient topology from there. It's sort of the same thing anyway. So we're gonna do quotient first. So after step 1, which is creating this product, or maybe just grabbing your R to the m-1, we're gonna define our equivalence relation, which we're gonna apply on our space here. So our equivalence relation is that a P inside R to the m-1 is inside the equivalence class of another point X. So P is inherently an m to the -1 dimensional point, so it is described with 196,882 coordinates, distinct coordinates from R1, okay? And that will be from another point X, which is basically the same, which has the same characteristics, but it's not the same on the nose. Now it could be the same as P, right? But the problem is, of course, we're having set contained inside itself, so that's not quite good because of process paradox. So we're gonna avoid that and say P and X are distinct. But in this case, we're gonna identify them if and only if there exists an integer. I will call it A. So this A exists inside Z. Now I'm not applying the subspace topology, but it's part of Z. That's the point. It's an integer, and that's such that, well, there exists an A inside the integer such that X minus B is equal to pi A. So it may not necessarily or strictly be 2 pi, but the point is each of these guys they differ by 2 pi A for A an integer. So X minus P divided by 2 pi is precisely an integer A. So if it's not that, then if that doesn't satisfy this case, then those 2 points they stay distinct or they're not identified. Okay, and this new identified point exists in M space, so R to the M. Okay, so they exist in a higher dimensional space, and of course, when we define this equivalence relation over R to the M minus 1, we get ourselves a quotient space. So that's our third step. What we're gonna do next is I'm gonna define this now as my T to the M minus 1, because we're describing these shapes via topological dimensions, the amount of dimensions a patch on the surface is, because of course we're talking about manifolds here, and a manifold is locally homeomorphic to a real space that is a dimension lower. So because our torus exists in 196,883 dimensions, then it must be that a patch on its surface is homeomorphic to a subset of R to 196,882 for it to satisfy the condition that it is a manifold, because of course a topological space can be anything if we don't specify what it is. So we're specifying that here this is a manifold. Okay, so going to the third step, I'm going to define this as the quotient space of R to the M minus 1 via this equivalence relation. And this tilde is precisely this operation we defined in step 2. And so this is the set of all equivalence classes of X. So one other way of denoting this, which is adopted from group theory, is R, or abstract algebra, you can say in general. M minus 1 mod the integers M minus 1. And how I'd like to think about this Z to the M minus 1 is that it implies that each identified point in R to the M minus 1 sort of differs in a way by an integer, but rather their difference divided by 2 pi is an integer. Okay, so that's just notation wise. We're giving hints towards abstract algebra, but we're mostly focused on topology, and I will give you guys the topological picture later. Okay, so this is the set of all equivalence classes of X, of course such that X is inside R to the M minus 1. Okay, so of course this only defines a set, right? And in order for it to be an actual topological space, which is a requirement for it to be a manifold, we need to define a topology over it, and then equip T to the M minus 1 with the topology, and then we have the final product. So that's our either your fourth step or your fifth step. Yeah, if you start out with just R here, it's your fourth step. Right now it's our fifth step because we did the product topology as our first step. Okay, so step 5 or step 4, if you chose to start out with R to the M minus 1, is to define the quotient topology. So the quotient topology, so this is where you guys can sort of skip the definition of a product topology here at the beginning, because you already defined it there at step 1.5 or something like that. But we're going to define the product topology along with this one here. So the fifth step is composed of defining two topologies rather, not two topological somethings. Okay, so we're going to define our quotient topology via all open sets U inside R to the M minus 1 mod tilde, which is T to the M minus 1. So I'm gonna put parentheses here, such that, you know, the set of all equivalence classes, or the set of all elements in R to the M minus 1. So this is another set here of x's such as their equivalence classes, so every point that they're identified with. So this is essentially a new point, so the equivalence class of x is essentially a new point in T to the M minus 1. And we're saying this here, every x inside our original space R to the M minus 1, and their identified points, or their new point in T to the M minus 1, is contained inside this open set. Okay, so all identified points with it, so the equivalence class of x is contained inside U, is open inside the product topology. And the reason why I'm saying the product topology here is because we did a product of r to the m minus 1. If we want to build this, if we want to bake this product from the ground up, we have to define every possible topology that we have done up to this point, or that could possibly be defined up to this point, because we cannot just define the quotient topology on its own, right? We need some underlying topology that we derive it from. And that is why the next part of the step is to define the product topology. So the product topology is the set of all products, so this is from I to the m minus 1 of open sets nu sub I, such that nu sub I, so each open set is open inside the topology of R. Because I cannot just define one singular topology that we say each, set of X inside R, dot 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 is inside of. I need to define step by step what exactly that topology is, with respect to another topology, which is sort of the bedrock topology, quote unquote, the bedrock topology, and that is the topology over the individual R1 spaces that we started with. So you can do this step, as I said a while ago, in the first step. You can define the product topology there and then sort of just skip over it and then skip onto the final construction. Okay, so after you've done this, you can define the topology over R to be any topology. It can be any topology. It can be the discrete topology or the indiscrete topology. But we mostly want it to be the indiscrete topology, most notably the Euclidean topology. Because the Euclidean topology is it's the most well-known and well-studied and well-behaved topology. You don't want any chaotic flavors in your donut when you eat it. So we want a topology that is well-behaved and it gives you the most depth. And that is the Euclidean topology. So with tau of R defined to be the Euclidean topology. Okay, so we're done with our fifth step. The sixth step is the final one. We're just going to equip t to the m minus 1 with our quotient topology, and then we're done. Oh, of course, you can say that you can use the other notations that I've introduced a while ago, or that I showed a while ago. Mod tilde tau q, and of course the space is that's with that. Of course, the notation for a topological space is independent, right? Unless that notation is for another topological space wherein it would differ already. Alright, so it doesn't matter how which way you define or use what notation in your final construction. Alright, so let's do a picture. Now I'm going to be using a dimensional cross-section of the actual space, because the actual space is something that we absolutely cannot visualize, okay? Because actual space exists up in 196,883 dimensions. So if we can't even visualize 4 dimensions, how will we visualize 196,883 dimensions, right? So I'm going to be using a 2-dimensional cross-section. You can use a 3-dimensional cross-section. That would give you a more complex thing, but yeah. Okay, so I'm going to pick a certain section of R2. So this is R2. And that section is I cross I. And then if we zoom in, we get this picture. So we have 1, 0, and we have 0, 1, this 1, 1, and then this, we're going to consider this rectangle here. Of course, this is 0, the origin. Okay, so what we're going to do is identify these 2 edges and these 2 edges. And this is in fact the geometrical construction of a torus in 3 dimensions. Okay, so a 3-dimensional torus, geometrically speaking, or a topologically 2-dimensional torus, right, or a 2 torus, is constructed via this. But notice that the real construction of our torus, of our monster donut, is something involving a hypercube of dimension 19688 2, right, yeah. Roughly the same topological dimension as our torus itself. Because this is a surface and the torus is already a surface, right? So yeah, we have 2 degrees of freedom. On the patch of a torus, there's another 2 degrees of freedom. Or it's still 2 degrees of freedom. So this becomes our torus, or our donut. But the real thing would be like a hyperdimensional space, so it's not visualizable. And this is only a 3-dimensional cross-section of it. Rather, 2-dimensional cross-section of it. Geometrically 3-dimensional, topologically 2-dimensional. So that'll be it for this construction, and I know it was a bit lengthy, but this gives us a more in-depth sort of construction over it, and probably more flavor than just doing a product and then sort of giving it a product topology. And so that'll be it for this tutorial, and hope you have a nice day and enjoy your rest, or enjoy your donut.